Excuse me, could you describe a situation when only one process on some machine fails? Not all the machine, but only one process.
So in the previous algorithm I presented, the model of Golub and Ramaraju, it is an individual failures model. So it's not necessarily the case that all the system fails, but you can have maybe just one process fail and then recover, or a few, etc., etc. So I don't know if this answers your question.
Yes, but how it can happen on the real hardware?
How can this happen?
Yes.
Okay, so I agree that it's easier to motivate a system-wide failure rather than a process failure. But you can think of maybe a large server with many CPUs. Maybe there's a problem with a single CPU. So then you only need to recover the processes that were running on that CPU, etc. But it's indeed easier to motivate system-wide failures. And indeed, the next thing I was planning to show is the recoverable mutual exclusion problem in a model where all the failures are system-wide and not individual. So I thought I had maybe too few slides for this presentation. So this is often the case with me. So last evening and night, I prepared more slides, and as usually it turns out I have too many slides in the presentation, but having white nights in St. Petersburg is natural. If not, then please read the story by Dostoevsky about white nights. So unfortunately, I need to skip this part about recoverable mutual exclusion under system-wide failures. I'll just give you the results. So there is work, and you have the references to this work in the slides, that shows that if you assume that all processes fail together, then you are not subject to the log over log n complexity, which is the best known when individual failures are allowed. Then actually you can take an algorithm such as Mello, Cramy, and Scott's algorithm and transform it into a recoverable mutual exclusion algorithm that satisfies the critical section re-entry property and other properties of, not all of them, of the MCS algorithm, and you can do that in a constant number of remote memory references. So you have the description and the references in the slides. Unfortunately, I won't have time to talk about that because I prefer to talk about models for non-blocking recoverable concurrent objects. So this is what we will start to discuss now. So I guess most of you, maybe all of you, are familiar with non-blocking algorithms. It's an alternative to lock-based, to blocking synchronization. There's a third alternative on which I think no one is talking in this summer school, but at the previous summer school there was one mini course about transaction memory, which I won't get into also, but it's another synchronization option for multithreading. So let's focus about non-blocking algorithms. I'll just give the required definitions, and in a later mini course by Michael Scott, he will elaborate on that and present some very nice non-blocking algorithms, but our focus here is about recoverable non-blocking algorithms. So who is familiar with Dean's notions of wait freedom, lock freedom, and obstruction freedom? Okay, so not all, so I will quickly go over that. When we are using a non-blocking algorithm, then we are guaranteeing some type of progress where processes do not have to wait for one another. So if we are using locks, then waiting for another process is inevitable, because if the process stays a long time inside the critical section, then we have to wait for it. And if it even fails inside the critical section, then we cannot proceed ourselves. But when we discuss the mutual exclusion problem, we assume that this does not occur. We assume that no process fails without being recovered inside the critical section or in the entry or exit section. But when we discuss non-blocking algorithms, we assume that processes may fail stop. That is, the scheduler will not let them take any more steps, never, but still we want the rest of the processes to make progress. So even if all other processes failed, then I would like to make progress. So this is actually the strongest non-blocking progress condition, which is called wait freedom, which means that every thread is guaranteed to complete its operation after it takes some finite number of steps, where steps can be reads or writes or stronger operation like cas, even if all other threads are very slow or even fail. So it's quite complicated to implement wait-free algorithms. So there is a weaker condition called lock freedom, which guarantees only global progress. So as someone commented during the break, the relation between wait freedom and lock freedom is quite similar to the relation between starvation freedom and deadlock freedom. So similarly to starvation freedom, lock freedom only guarantees global progress. So if a process takes more and more steps, then eventually some process will complete its operation, but not necessarily this process. So starvation is possible. And again, the difference between the two sets of models and definitions is that in the mutual exclusion problem or setting, we assume that a process always gets the chance to perform the next step, whereas when we discuss non-blocking algorithms, we assume that some processes, maybe all except one, may eventually stop taking steps. So the scheduler is not fair. And there's even a weaker condition called obstruction freedom, which is much easier to implement, but it only ensures that if some process runs alone, taking steps by itself, that is solo, long enough, then that process will finish its operation, but this condition does not preclude scenarios of live lock if a few threads are performing concurrently. Okay, so we already know the compare and swap operation. Is everyone familiar, or sorry, that's not the right way to ask it. Who is familiar with Treiber's stack algorithm? Okay, so I'll quickly go over it in order to introduce some concepts. So let's see a very simple non-blocking algorithm that was originally published in a manual by IBM, but then a different version was published by a researcher called Trieber, and the algorithm is called the Treiber algorithm since then. And it implements a leaf for a stack, and the stack has a top, which is a pointer shared memory variable that points to the top of the stack. And each element in the stack is a structure with two fields. Val stores the value of this item, and next points to the next item in the stack. So how would we implement the push and pop operations in a non-blocking manner? Well, when we have cas, when we have compare and swap, this is quite simple. So for example, to add a new item to the stack, we simply allocate the memory for the new structure. We initialize the val to the correct value that we want, and we set the next pointer of the new node to point to the node that is currently pointed at by the top global variable. And then we perform a compare and swap, an atomic compare and swap operation, trying to swing the pointer atomically to the new node. If we succeeded, then the operation occurred and the new value is in the stack, the new item is in the stack. If we fail, then we will try again in another iteration of a loop. So let's look at the code of push. It's very simple. We receive the stack S and the value V we would like to insert to the stack, and we create a new node, we initialize the value to V, and then we iterate again and again, and in every iteration we do the following. We read the current value of the top pointer. We set the next pointer of the new node to point to the current top. And then we try to swing the pointer as we saw before by performing compare and swap. If we succeed, then compare and swap returns true. And so the operation returns because the item was inserted into the stack. Otherwise, we will try again in another iteration. So what does the opposite operation, that is pop, do? Well, it does what we expect it to do. It tries to atomically perform a compare and swap on the top pointer so that it will point to the next item in the linked list that represents the stack. It might be that the next pointer is null because there's just one item in the stack, in which case this cast tries to atomically set top to null, that is to make the stack empty. If the compare and swap succeeds, then we are done, and we can simply return the value in the item that we removed from the linked list. Otherwise, we reiterate, we try again in another iteration. So here's the code, also quite simple. In a loop, we do the following. We read the current value of the top of the stack. If the stack is empty, we return an empty indication. Otherwise, we try to do this atomic compare and swap, and to swap the value from the current value t that we have just read in line 2 to the next pointer. If we succeed, then we simply extract the value from the item we removed and return it. Otherwise, we try again. Now, this algorithm is lock-free. It's not weight-free. Why is it lock-free? Yes, so the algorithm is lock-free because there is a global progress. And if we assume, let's look at an iteration of the pop or the push, it's the same logic. If the compare and swap here succeeds, then there is progress, because this means that this operation actually took effect. It occurred. But if the compare and swap fails, this can only be because between reading the top in line 2 and attempting the compare and swap in line 5, some other compare and swap operation managed to change the top variable, which means that that operation actually succeeded. So this means that this very simple algorithm provides global progress. So it provides lock freedom. However, it does not provide weight freedom, because the same operation can fail in line 5 again and again, while other operations keep succeeding. So there may be kind of starvation in this case, which means that the algorithm is not weight-free. Okay, this is just to bring back to your cache, or maybe to those who are not familiar with the terms, the notions of weight freedom, lock freedom, which are relevant to this part of the talk. Okay, so we saw that the algorithm is lock-free, but we also want to show that the algorithm is correct. And the question is, what does it mean for a concurrent algorithm to be correct? So before starting this description, who is familiar with the term linearizability? Okay, so about half of you, so I will explain this notion anyway. It's easier to be familiar with the term linearizability than to say it fast. You can try it after that to say linearizability. Anyway, The problem is that when we talk about the correctness of a sequential object, it's generally clear what we mean by that. For example, consider a counter that supports a single operation of fetch and increment, and assume that this counter is being accessed sequentially. So only one thread performs fetch and increment operations on the counter, and there is no concurrency. Then we know that that operations on this counter, assuming it is initialized to 0, will return a sequence of value that are consecutive starting from 0, 0, 1, 2, etc., etc. And it is clear for us what it means that one operation comes after the other, because the execution is sequential. So before the next operation starts, the previous operation has to terminate. So we have full order between operations applied to this sequential counter. But what happens when we have concurrency, when we have several threads that can invoke fetch and increment operations on the same concurrent counter? Now we no longer have a total order between the operations that are performed on the counter. So for example, in this figure, we have 3 threads that are invoking fetch and increment operations on the concurrent counter, more or less at the same time, and then we have another fetch and increment operation by the second thread applied to the counter. And observe that in general, the execution of the operation, it's not a single read or write. It's a sequence of read or write or compare and swap operations. So this is actually an interval in time that starts when the operation on the counter is being invoked. Then there is the execution of the algorithm that implements the fetch and increment operation. And finally, there is the response. So these 3 operations are concurrent. So we can't say who comes before who. So how do we know if this execution is legal, or maybe it's illegal and our implementation is not correct? So let's see. Assume, for example, that these 4 operations return values 0, 1, 3, and 4. Then for sure we know that the implementation is incorrect because we have skipped the value 2. There's no way we can arrange the order of these operations to get a legal execution of a sequential counter or legal history of sequential counter, because as we saw, this must be a continuous range of values starting from 0. So this is clearly incorrect. If our algorithm has such an execution, we can conclude that it is incorrect. So let's consider now this case. So in this case, the values that are returned are indeed continuous starting from 0, so there's no problem from this regard. However, here we have another problem. There are 2 operations here. The operation that, Okay, so why is this incorrect? Sorry. So this is incorrect because we have these 2 operations over here between which there is an order, because this operation entirely precedes this operation. That is, the response of this operation precedes the invocation of that operation, but the value returned by the earlier operation is larger than that returned by the later operation. So we also regard such an execution as being incorrect. However, we regard execution such as this as being correct because what we can do is we can extend the partial order of the operations in the execution by defining an atomic point that we call a linearization point inside each operation, so that the order of these points defines a legal sequential execution, in this case 0, 1, 2, and 3. So this is a correct execution, and more formally, we say that this is a linearizable execution. We'll see the formal definition in a minute. Sorry. And if an algorithm only generates executions such as these that are linearizable, then the algorithm is correct. That is, it is linearizable. Yes, there was a question there? Okay. So formally, we have this definition, but it doesn't say anything more than what I just shown you. So if we are able for every execution to order the operations in the concurrent execution in a total order that is consistent with the partial order in the concurrent execution, that is, if we can find linearization points in each of the operation, and we get a sequential history that is legal, then if we can do that for all the executions of the algorithm, then the algorithm is linearizable. And this is the most commonly used correctness condition for concurrent objects. So there are a few examples here. I'll just show the second one. So is this linearizable? Assume that we now have a FIFO-Q with NQ and DQ operations. Is this execution linearizable? No, it's not linearizable because we have NQ of X preceding DQ of Y, but we only have a single, preceding NQ of Y, but we only have a single DQ which extracts Y from the FIFO-Q. So there is no way we can order these three operations while maintaining the fact that the NQ of X precedes the other two operations and receive a legal sequential execution. So this is illegal. If our algorithm has such an execution, then it's a non-linearizable implementation of a FIFO-Q. So let me skip some other examples. Okay. So two things to note about the definition of linearizability. First, we assume that thread histories are sequential. That is, every thread performs a sequence of invocation and then the corresponding response. Okay, it cannot be in the middle of performing two operations concurrently. Secondly, we are allowed to remove pending operations. So if some operations did not terminate, for example, this pop operation, then in some cases we are allowed to eliminate, to remove this operation altogether, and it's enough to have a linearization, a total order without this operation that actually did not yet happen. It did not yet take effect. Yeah. So let's go back to Treiber's stack algorithm. So the linearization point, we were asking ourselves whether this algorithm is correct or not. So now we have the answer that if we can linearize every execution, then the algorithm is correct. And it's easy to see that the linearization point for the push operation is here when we succeed, if and when we succeed to perform the concurrent swap and actually insert the new item to the stack. And similarly, in the pop operation, when we manage to extract the item from the top of the stack. But there is another linearization point here in case the operation returns an empty indication, that is when the FIFO-Q is empty. And then at what line will this linearization point be? So I had 2 and I had 3. And the answer, the correct answer is in line 2. Because in line 2, we read the value of top, which we later find that is null. So at this point, we know that the stack is empty. But we cannot say that the linearization point is in line 3, because it may be that between the execution of line 2 and line 3, the queue becomes full again. A few NQ operations succeed. And so returning or putting the linearization point of returning empty here is not correct. It's not a correct linearization because at this point, as I said, the queue may be non-empty once again. So the correct linearization point has to be at line 2. Okay, so why am I talking about linearizability? The reason is that when we discuss the new model of failure and recovery, then we need to revise, in some sense, the definition of correctness. And why is that? Well, first of all, when we just discussed linearizability for the regular model, we saw that every thread history is well-formed. That is, it is composed of a sequence of invocation and the corresponding responses. But in the failure recovery model, this is no longer the case. So for example, consider this concurrent execution of, let's say, these two threads that operate on two objects. And take a look at the upper thread here that fails in the middle of doing a push on object 1. After it recovers, it may, in principle, start to perform another operation before there is any response to the previous operation. So this is not a well-formed thread history. So obviously, we can maybe deal with this problem by just removing from the history all the operations that failed. But in general, we cannot do that because it may be that the operation actually succeeded to have its effect on the concurrent data structure before it failed. For example, it may be that this push operation succeeded with its concurrent swap and then failed before returning a response. So we cannot just remove it from the linearization because we see here there is another operation that does not fail and returns 0. If we remove the push of 0, then we can no longer find the correct linearization. So we have some problems here with the definition of linearizability that we need to somehow resolve in order to be able to reason about the correctness of recoverable algorithms. Any questions up until now? Okay, great. So there were quite a few definitions of correctness conditions for recoverable concurrent objects. For example, Berry-Hill et al. Defined recoverable linearizability, saying that an operation that fails can be linearized before the subsequent operation on the same object by the same process. So a process may fail and then recover, and then the linearization point of the failed operation can come later on as long as it occurs before the next operation by that process on the same object. And there are other definitions in addition to those I show you here, but the common feature of all these definitions is that they only worry about ensuring the correctness of the objects after the failure and recovery. So all these definitions that are deemed here and many other do not worry or do not guarantee that once a process performs an operation that fails, the process is able to recover and know whether its operation took effect or not. Did my pop succeed or did it not? And if it did succeed, what value did it return? So these correctness conditions do not guarantee this knowledge. And so a few recent works define the notion of detectability, first defined by Friedman et al. in PPOP last year. And detectability means that in addition to maintaining the consistency of the concurrent object in the crash recovery model, we also need to make sure that the thread is able, when it recovers after the failure, to know whether the failed operation took effect or not, and if it did, to know what value it returned. Another work by Ben David et al. Appeared in PPOP this year, but actually it was as a technical report also in 2018, defined a similar notion. I will discuss about a formal definition of this concept that also allows us to compose recoverable objects. That is, if we have base recoverable objects that are linearizable according to this definition, we can use them in order to implement more complex recoverable objects. And this is called nesting safe recoverable linearizability, or NRL in short. So let's get to the definition of this correctness condition, and then we will see how we can implement an object that is recoverable according to this definition. Okay. So, in a sense, we can view this model of nesting safe recoverable linearizability as an extension of the model for mutual exclusion that we saw, the model by Golub and Ramaraju. Also here we assume that every write is persisted, so we actually assume that caches are persistent, they are non-volatile, and we assume that individual processes may crash fail. When they do, all the shared variables, the values are retained, but as before, all the local variables, their values are lost, actually initialized once again. So if we performed a read or a fetch and increment or a swap operation, and we failed just when we were about to perform this operation, the question is, how can we know whether the operation took effect, and if it did, what value it returned? So now we associate with every operation that we can apply to the concurrent object a corresponding recover function. So for example, if we have a FIFO-Q with an NQ and DQ operations, we associate with each type of this operation a corresponding recover function. And in general, the execution may be nested. This is why we call this nesting safe recoverable linearizability. So we may have one recoverable object calling an operation on another recoverable object. So what happens when there is a failure, when some process fails? Then we assume that the system has some support that invokes the innermost recovery function for the operation that failed. Okay, so if we have one operation, op1, which is recoverable, invoking another operation, op2, also recoverable, we will consider for simplicity that all operations are recoverable, and then there is a failure, then the system will invoke the recovery function for operation op2. This implies that the system must maintain in persistent memory actually the stack frames that led us to the last invocation and the value of the program counter at the point of failure, although this assumption can be relaxed. So now, in terms of the history of an execution, we don't only have invocation as response step and response steps as before, we also have crash steps and recovery steps. So an invocation step as before tells us that some process P invokes some operation op on object O. Similarly, response tells us that the process P receives a response of threat from the operation invoked on O. But now we can also have crash steps that signify that specific processes fail, and corresponding recovery steps saying that the process is recovering from the failure. Now, you should bear in mind that while attempting to recover, a process may fail once again, and this may occur maybe multiple times. So recovery steps means, as I said before, that the system invokes the recovery function corresponding to the innermost operation that was active while the failure occurred. So in order to make these definitions more concrete, let's see an example. So the example is a sub-history of only a single process. So assume that first this process invokes operation op1 on object O1. Okay? Now, this recoverable operation is able to invoke another recoverable operation, so we get a nested execution. So the next thing that occurs is that this process P invokes another operation op2 on object O2. Okay? So now there is a crash. When this crash occurs, eventually we will have the corresponding recover step, meaning that the system invokes the recover function that corresponds to the innermost operation. In our case, this is operation op2. Now maybe there is another crash. So while the recovery function is in the midst of executing, we may incur another crash, and then eventually we will have another recovery. And this may continue one or more times, but hopefully eventually there will be sufficient time for the recover function to complete its operation, so finally op2 will return its response. Once it does, we are back into the execution of operation 1 on object O1, and we may incur another crash, but this time, to recover, the system will call the recover function that corresponds to op1, not to op2, because we're already out of op2. And finally, op1 returns a response, and that's the end of this execution. So these assumptions by the model actually imply that if we are failing inside a recoverable function, the system will try to complete it again and again until eventually, hopefully, it succeeds in doing so, and then we return to the upper level function. So if we get such a history, and looking here, we see that this is a multi-object history. We have two objects here, O1 and O2. Generally, when we consider linearizability, maybe we look on a single object history, but since we are talking about nesting, we must consider multi-object histories. And in general, of course, this will be also multi-process histories. Here we only see a sub-history of a single process. So what does this mean for such a history to be NRL, that is nesting safe recoverable linearizability. It means that the history is well formed. What do I mean by well formed? For every operation, we have its invocation, then we have possibly a sequence of crash recover events ending by a recover, and if we are lucky, this is eventually followed by a response. But we're not allowed to have, for example, 2 consecutive recover steps without a crash in between them, and we cannot proceed, the same process cannot proceed to perform the next operation because before it receives a response for another operations unless these operations are nested. I won't get into the formal definition of that, but more intuitively at a high level, we say that a finite history satisfies this condition if it is well formed, and if once we remove all the crash and recovery steps from the history, so here we remove them, then we are left with a regular multi-object history. And if the history on any of these objects is linearizable, then the original execution is linearizable. So this is, in terms of linearizability, this is actually implied by the locality property of linearizability that states that if a multi-object execution is linearizable if and only if the projection of the execution on any object is also linearizable. So actually what we are saying here is if the execution is well formed, simply throw away all the crash and recover steps, you are left with a multi-object history. So consider the history on every object separately. If all of them are linearizable, then so is the original execution. Okay, so how do we create, how do we write an implementation of an object that is non-blocking and satisfies this requirement? So as I mentioned before, the key challenge is to deal with the cases in which an operation invokes a read or a write or some other read, modify, write operation, or even invokes a function, and then there is a failure, and we must make sure that the recover function is able to know more or less where the failure occurred, and either to conclude that the operation already took effect and then return the correct response, or to infer that the operation has to be attempted once again. So I will show you how we can implement a recoverable version of concurrent swap. Now, why do we need recoverable concurrent swap? Well, if we have some algorithm that directly invokes a concurrent swap operation and then there is a failure, then it is not clear how the invoking operation, when it recovers, concludes whether or not the case took effect. So we can either deal with this separately for every operation that invokes concurrent swap, or we can have recoverable functions invoke a recoverable version of concurrent swap, and then we can be assured that the invoking operation will be able to determine if the concurrent swap took effect or not, and if so, to receive the response. So let's see this algorithm, which provides the code for process I. So as usual, we assume we have n processes with identifiers 0 through I minus 1. And to implement this algorithm, we have a shared regular CAS register C, which is not recoverable, and is initialized to the value, to the tuple of value null, comma, init. So this, these two values have the following semantics. The right-hand value is the actual value of the CAS, the application value. And the left-hand value, initially null, is the identifier of the process that wrote that value. So initially we have the init value, and it was not written by any of the processes. The reason that we need to know who wrote the last value is in order to allow that process, when it recovers, to know whether its CAS succeeded or did not succeed. We'll see in a minute how this is done. So we make an assumption that all the values written by the process are unique. So this can be, this assumption can be implemented by, for example, having each process append to the value it writes some timestamp that increases from one write to the other. This seems like an artificial requirement, but actually we have other work that proves that in models for recoverable objects, we sometimes must, at least for some algorithms, including CAS, we must either provide such information or make assumptions like this one, or we should receive other information from the system. But this is not for this talk. Okay. So again, we have this variable C initialized this way, and we also have a two-dimensional array R, all entries initialized to null, that allows us to implement a helping mechanism through which a process will be able to conclude whether its concurrent swap operation succeeded or not. So let's see how this is done. So to perform a concurrent swap operation, the arguments, as always, are an old and a new parameter. Recall that both of them are pairs of values such as that one. So the CAS starts by reading the current value of C, which is the pair of values J, a process identifier, and the value, which is the current value of the concurrent swap object. So if the value is not equal to old, then the concurrent swap operation can simply return. Okay? It is doomed to fail, so it can return false, because the current value of the object differs from the old value, so it should fail. And in this case, what would be the linearization point? Yeah, it will be line 2. When we read that the current value of the CAS object is val, and val is different from old, then this is the linearization point at which the CAS return false. Okay. Otherwise, the CAS may succeed. So what we do is we check who wrote the last value val, and recall once again that the values written by every process I are unique. So if this is not the initial value, then J is not null, so the last value was written by process J. So what the current process does, it reports to process J in the entry R of J and P that it saw value val. This will be a proof for process J that its operation took effect. So if J later fails and then recovers and is not sure if its write of value val succeeded or not, it will be able to read the proof for it in this entry of the R array. And only after that, the process attempts to compare and swap the previous value it read, j comma val, with the new value it wants to write, p comma new. And again, it writes here its identifier so that it can be helped if it fails immediately before or after performing line 7. Finally, the compare and swap operation returns value read. Now, the read operation is trivial. We simply read the current value, which is a tuple of C, and we just extract the second value and return it. Nothing interesting about this operation. So now, as we said in this model, each of the operations has a corresponding recovery function. So the cas operation has a corresponding cas recover function, and similarly, the read operation has a corresponding read recover function. But recovering from a failure inside the read is not interesting. You can simply read again. So we don't see the code of the read.recover. We only see the code of the recovery from a failure inside the compare and swap operation. So I forgot to mention before that the recovery function is called with the same arguments with which the failed operation was called. So cas.recover is called with the same old and new arguments that was passed to the cas operation that failed. And I remind you that it is only called if there is a failure while this operation is performing. So what the process does in line 13 is it reads both the value, the current value of C, which is p comma new, and all the values that were reported to it, that is all the value in its row in the R array. So if any of these values equals the new value that the failed operation tried to write, and I remind you once again that we assume that all values written by the same thread are distinct. So if this is the case, then the recovery code or the recover function knows that the failed cas operation failed only after it performed a successful compare and swap operation. So the recovery code can return true. Otherwise, we are not sure whether the operation took effect or not. Sorry, we are sure that the operation did not take effect. Otherwise, someone would have reported to us that it saw the value that we tried to write, or we would see it in variable C. So the recovery code simply proceeds to re-execute the code of the cas operation. So note that this code will work correctly regardless how many failures you would have inside the cas or inside the recovery code for the cas. So if you have a well-formed history, including the invocation of the cas and then a sequence of crash and recovery steps, eventually, if there will be no more crashes, no more failure, then the response will be returned. And we assumed that the response is returned when the operation is completed either directly by the original cas operation or by the recovery code. So one of the exercises that I have prepared relates to this pseudocode. So there is a subtle point here which I will not touch now unless anyone forces me to do so, which is an exercise. Don't kill my exercise. Yes?
Question?
Yep.
I have a hard time to understand why. How can it happen that you have C which doesn't store the value but someone reported...
Okay, an excellent question. Okay, so it may be the case that a certain CAS operation by process P succeeded to perform this concurrent swap, and then it fails. Let me remind again that this is a generalization of the model by Golub and Ramarajo, also in the sense that failures are individual. So it may be that before this process recovers, another process comes and changes the value of C to another value. So when the recovery function is called, C no longer holds the value that was written here. But in this case, the value will be in one of these entries. So this is the helping mechanism that allows a process to recover always. More questions about this code or the model itself?
Why do you need n variables to store the old ones in case of crash? Don't you just need the last one?
Are you asking why do we need a two-dimensional array?
Yes. Don't you need just one dimension? Don't you need just the last one?
Actually, that's a good idea for another exercise, but one, unless I'm missing something, a one-dimensional array will not work because if all processes help process P by writing to the same location, then it may be that an old operation is about to write a stale value in this location, and it will overwrite a more recent help by another process. So if you look at this code carefully, you will see that you must have each process I being able to help every other process J in a separate location I, J.
Yeah, sorry.
You have the microphone, so
yeah, I have a privilege. So, coming back to my original question, if you imagine that you don't find your value in C, yeah? Mm-hmm. you execute the compare and swap recover procedure. Isn't it safe to return false immediately?
If you don't, no, it's not. So the question is, if we don't find, let's say that this CAS operation wanted to do a CAS from 10 to 17. And this CAS actually succeeded, but immediately after that, this process I, let's say, failed. So now the value of C is 17. Now comes another process and replaces the value, does a successful CAS that replaces the value from 17 to 20. Only then the recovery of process P occurs. Now process P will not find the value 17 inside the first component of the second, component of C. But the process that replaced P's value will write the previous value to the corresponding entry in the line corresponding to P in the R array. So P will be able, after it traverses this line, to conclude that indeed its value has been seen by another process. Hence, since we assume that written values are distinct, the value was indeed written. Yeah.
Can we just return, on the line 15, after else, can we just return false and be happy?
Okay, a good question. Can we just return false and be happy? We can return false but be unhappy because it will be incorrect. because let's say that you are about to perform a compare and swap between 10 and 17, and then there is a failure. And indeed, the value of C is 10. Now here you're checking whether value 17 is currently inside C. So the value 17 is not there, and it's not, yeah, so maybe I'm missing something here.
I think we should define here what is the meaning of the false.
No, returning false means that there was some point in your execution interval. No, you can't return false. Returning false, let's see. Returning false means that your compare and swap operation did not occur.
And it didn't. And it didn't.
No, did not occur, but it did not occur and shouldn't have happened. That is, if the value of cas equals old, if the value of the cas object equals old, then the cas operation is not allowed to return false. So assume that the value, once again, the cas is between 10 and 17, and it is 10 all throughout the execution here, but there is a failure at this point, and then what the recover does, it searches for the value 17, which is not there, hence the recovery function returns false. But since the value of the cas object is 10, all along this time interval, the cas is not allowed to fail. It must succeed. Yeah, exactly. But it was a very good question because it got me somewhat confused. So, more questions?
Yeah, if you please. Why after before we return through on the line 14 we do nothing?
Can you raise your hand?
Yeah, I'm here.
Yeah. Okay.
Yeah. Why when we found that in our entries definitely there is our value, why we do nothing before return through?
In what line?
14.
In line 14.
Yeah, we found that
okay.
the new in our
this
entries.
is because we assume that all values written by any single process are unique.
Okay.
So if I see value 17, I only write it once. This means that this is, and this is a value that was reported to me. So someone saw that I wrote this value. So I can rest assured that indeed my compare and swap operation succeeded.
Yes, but we didn't write it in C.
We didn't? What?
Or didn't write the new value in C. Didn't we?
I didn't understand.
So the cas means compare and set, right?
Compare and swap, yes. Mm-hmm.
And swap, yeah. And my understanding is that at the end of the day, we want to see in the C entry the new value. If
yes, and it was. It's currently. I mean, if you see that new is not currently in C, but it's in one of these entries in P's array, then you know that this value was written, and later on it was overwritten, but it was written. And so before the failure, the cas recoverable operation succeeded to write this value, so we must return true. Although the value was overwritten since then, but that's okay. That's exactly the problem that requires this helping mechanism, because without it, there's no way for process P, if it fails immediately after performing line 7, to infer that the cas indeed succeeded.
Okay, got it. Thank you.
Okay, so just so that I have time. Okay, there is some more time. Yeah.
Should all the recovery operations we write be idempotent?
Should all the recoverable operations be idempotent? Not
Yes.
necessarily, no.
But if we get some crash in the recovery operations, and then we recover and do another recovery operations, and if they get a conflict?
No, the recovery operation itself can record in shared variable the state of recovery. And so if recovery proceeds, then if there's another failure and then another recovery, then the later invocation of the recover function can know at what point the the later failure occurred and continue from there. So there's no requirement that the recovery code will be idempotent in general, no.
And is it correct that if we get a crash in cache recover, we start cache recover again when we recover?
If we crash inside
inside the cache recover.
Yeah. If we crash inside the cache recover, it's equivalent to crashing inside the operation itself. And the next time we recover, the recovery code will be invoked from the beginning.
That's why it should be idempotent, no?
From this regard, yeah, you're right. This code may be executed several times. The state may change from one execution to the other, but correctness must be maintained. Yeah, you're right. Correctness must be maintained even if this code is invoked multiple times. Yep.
When we search new in array, why do we search only for process P, not for all the processes?
Why not what?
Now, why do we search only for process P and not for all the processes? May I understood correct? That when we search a new value in array, we search in array for only process P and all values that it set it before. Am I right?
So every line 13. Okay, why is it P? Because this is the code for, okay, sorry, my mistake. It says it's process I, yeah, it should be process P, sorry, my mistake. So this is the code for some process P. So every process searches in its own row. So when it reads C, it checks whether its identifier is written there. And when it scans the helping array R, it scans the line that is its own line. So my mistake, I should be actually P. Yep. Okay. So it can be shown that this implementation satisfies the condition that we defined before, namely the NRL, the nesting safe recoverable linearizability. And it can be shown that in the lack of failures, the recover function completes in a linear number of steps and all other operations complete in a constant number of steps. So in general, we can take every algorithm that uses compare and swap, and if we want to make such an operation recoverable, we can replace the invocation to regular compare and swap to invocation to recoverable compare and swap. We should, by the way, do something similar for read-write registers, but let's not get into that. So this means that we can essentially have a universal construction for our recoverable objects, but this will not necessarily be the most efficient implementation. So there are already published papers about implementing detectable recoverable algorithms. I remind you that detectability means that post-failure we can determine whether the failed operation took effect, and if it did, what value it returns. So there are implementations of more interesting objects, linked list-based sets, elimination stacks, etc. There are recoverable implementations of such objects. In the same work, we also presented the recoverable version of a read-write register, as I mentioned, and also of a test and set operation. And interestingly, this model also allows to reason theoretically about the properties of such implementations. And for example, it can be shown by using a technique called valency arguments. For whoever is familiar with that. If you're not familiar with that, it's not essential for this talk. It's just a proof technique that allows us, in this case, to prove that you cannot implement a weight-free recoverable test and set if all that you have in your disposals are read, write, and test and set operations. So this is a theoretical result. It will not help you implement a more efficient algorithm in your machine, on your NVRAM-based machine, but theoretically it's interesting. And what it means that there's no way of implementing a weight-free recoverable test and set. Specifically, this means that either the test and set operation or the corresponding test and set recovery function, at least one of these cannot be weight-free. Okay, so far I have discussed a few models for systems that can use non-volatile RAM in order to recover. First, I discussed models for the mutual exclusion problem, and then I discussed a model for non-blocking algorithms, so that in that model we can implement in the modular manner more complex recoverable objects from simpler recoverable base objects. But these are relatively abstract models, so the question is, what is there really out there in reality? So let's do a quick reality check. Reality checks tells us that NVRAM-based systems are already here. So they are commercially available for a few months already. So there is a very comprehensive and interesting performance evaluation of this system in the reference given here by Israelevich et al. If you're interested in the performance of such systems, then you're warmly invited to read this paper. I guess there may be also others. And in the system that they evaluated, there are two advanced models of Xeon processor. Each of them has 24 cores. They had this amount of memory in DRAM, but quite a substantial amount of memory in PMM, which is a persistent memory model. This is actually the technology, the memory technology that can be used for non-volatile random access memory. So this is how the memory card looks like. It's called, it's an Intel technology. It's called Optane Data Center Persistent Memory. Let's call it just a PMM, a persistent memory module. And each of these cards can store 128, 256, or 512 gigabytes. Each of the cores, so each of the CPUs can host up to 6 such DIMM cards. So altogether, you can have up to 6 terabytes of main memory, which is quite nice even for a hard disk, and certainly so for main memory. In this case, they only have 3 terabytes because they use the 256 giga memory cards and not the larger ones, but still it's a substantial quantity of memory. So it turns out that you can configure this new type of memory, which is based on technology called 3D crosspoint from Intel. You can configure them in one of two modes, either in memory mode or in what is called the up-direct mode. So in memory mode, you actually use the new type of memory, the PMM. You use them as regular non-volatile main memory. And actually, in terms of the system, both the operating system and applications, they only see a larger amount of main memory, which, as far as they know, is a regular DRAM. And the DRAM in the system is not just thrown away, it actually serves, when the system is configured in this way, it is served as a write-back cache behind the new category of memory, behind the PMM. So you have a very large cache, which is the DRAM, that sits behind the new non-volatile RAM. So effectively, what you get is a very large main memory with performance that is not very far from the performance of DRAM. And for many applications, this is already very significant and very important. But the mode that is of more interest to us in the context of recoverable algorithms is the mode that is called UpDirect, where you can access separately the DRAM and the new memory, the obtained persistent memory. Okay? So you can mix these two types of memory and you can access DRAM directly. And we'll discuss in a minute how you can access the new type of memory, that is the PMMs. Okay, so when you configure this memory as UpDirect, you can configure it either in UpDirect block mode or as persistent memory, which is exactly what we mean when we talk about non-volatile RAM. So when the persistent memory module is configured in block mode, this is also called storage over UpDirect, then you still access this memory as a substitute for a disk, a very fast disk. So the file system does not have to know that this is not a regular SSD disk. It simply works with the appropriate driver to access the new memory. And applications do not see anything different. When they want to, they cannot read or write to the non-volatile memory as main memory. They can only access it as files through the API of the file system via the kernel. However, the second mode is, as I said, is called persistent memory mode, and this allows the applications to access specific addresses in the persistent memory, and it also allows file systems to be optimized to access this memory not in block granularity, but rather in finer granularity of, actually granularity of the cache line. So when the PMM is configured this way, and file systems that support this type of access are said to implement the DAX property, that is direct access, then these file systems, as I said, if they have above them applications that what they typically do is they perform random accesses to files, small writes here and there, then performance can be optimized in comparison to more standard file systems that always write in byte granularity. But what is most interesting for us is to have the applications themselves write directly to addresses that are mapped to the new non-volatile RAM. And this is done, this can be done either directly or by using a set of libraries provided by Intel, which is called the PMDK, Persistent Memory Development Kit, which provides all kinds of services that make it easier for you to work with this new type of memory. Now, yeah, we'll get to this in a minute. But the key difference between the models I described to you in this mini course, and the reality that we see on these machines is that caches are volatile. Okay, and we assume that caches are non-volatile, that every time you do a write, this write gets persisted, and if there is a failure, then when the system or the process comes up again, it will see the written values updated. This is not the case in this system because it guarantees that stored are persisted only when they get through the caches into this area, which is called the power fail protected domain. When a write arrives here, even if it's not yet written to the actual persistent memory, but rather to this kind of write queue or write buffer that is inside this zone, when a store arrives here, then you can guarantee that even if there is now a power failure, there is enough power left in the capacitors of the system to push the values here to the memory. So everything that gets into this zone is guaranteed to be persisted. But since you may perform a write to the cache, and the value can remain in the cache maybe for a long time before it is ever written to the main memory, if there is a failure in this point, you will lose this value. It will not be persisted. So this means that applications need to take care themselves. That is, applications that would like, for example, to implement the recovery code according to the model or one of the models that I've shown you. If they would like to ensure correctness, then they must, in certain places, make sure that values that were written are flashed from the caches into this area, and they should be flashed in the correct order so that the correctness of the algorithm is maintained. So if you just do a bunch of stores and you don't ensure that they are evicted or at least flushed from the caches and get here, then you cannot rely on being able to see these values after you fail and then recover. So in order to allow you to perform the correct synchronization so that when you perform a sequence of stores, these stores will be persisted to the NVRAM and they will be persisted in the correct order, then there are several instructions that are available on these types of machines. So the sfence is an instruction that is also available for a long time on other Intel machines. It's a store barrier. It simply ensures that all the stores that you performed in the program order before the barrier get globally visible before any store that comes after the store barrier. So that's a standard. There's also an instruction, a standard instruction that is called CFlash, which simply takes an address and flashes the cache line containing this address to the main memory through all the levels of the caches, and this cache line is actually evicted from all the caches. So CFlash exists on previous systems, but here they have an optimized implementation that is called CFlash opt, because there are some applications of non-volatile RAM that have to flash a relatively large area of addresses, range of addresses, to the persistent storage. So in this case, you need to perform a sequence of CFlash operations for a few cache lines. And this instruction is optimized to make these CFlashes concurrent, rather the previous implementation, which is much more sequential. So as the paper that we saw, the experimental evaluation shows, indeed this performs better than the non-optimized C-flash. Finally, or almost finally, it's also the instruction of cache line write-back, which is similar to C-flash, except that the cache line remains valid. So it only makes sure that the value that you wrote gets to the persistence area, so you know it is persisted, but the cache line is in general still valid, so you may get less cache misses if you use CLWB, which is also a new command, rather than if you use C-flash opt. There's also non-temporal stores. I won't get into this, but the key idea is that Intel made an effort, and actually in accordance with the standards defined for a non-volatile memory, there's a standards body called SNIA that defines these standards to support the appropriate synchronization instructions that can make your code correct in this system more efficiently. And let me just say that all these instructions are user-level instructions, so you don't need to call into the system in order to perform these synchronization operations. So there is, as I said, the difference between the more theoretical, more abstract model that I've shown and the real system, but it may very well be that in a few years, also the caches will be non-volatile. There are a few key Intel engineers that think that this is about to happen, in which case the currently abstract model will be actually much more realistic. And just to give you an impression of the performance overhead, that the new category of memory, the PMM, incurs relatively to DRAM, so it's not too bad if we compare the latency of random load operations, then this is about slightly less than 4 times slower. So it is slower, but not in orders of magnitude. If we compare swaps, then the gap is even smaller, much smaller. The reason is that if we return to this figure here, then they don't actually have a way to measure whether the store reached the memory itself, only if it reached this zone. So maybe it only reached the right buffer, but then for them, the store already succeeded. I guess this is why the difference for the stores is much smaller. Anyway, you are indeed invited to read this survey about the comprehensive evaluation of performance, and you will see that quite several applications perform significantly better when they run on this system in comparison than when they run on smaller DRAM. Yep.
Is it known for how long NVRAM can store data without power? Like hours, minutes, days?
I would say like SSD, so for years. Yep. Yes.
Yes, I have a question about C-flash spot, if you could return back.
Yeah.
So it is optimized for concurrency, but I see the problem with hyperthreading. It is an Intel technology. So we have one cache for 2 threads in the same time. And is it right store data or load data for that 2 threads on one core?
Say again.
It is about hyperthreading. So we have one core
hyperthreading.
And
okay.
2 threads on this core, and we have a shared cache for that. So is it a problem for this function because it is optimized?
It does this per logical thread. So for Each logical thread has its own different program and program order. So when one logical thread, you may have the performance of other logical threads that share the same cache if you do the flash, but if you only do the CLWB, then you will not cause the other thread to incur more cache misses. You will only make sure that the value that you wrote gets to the persistence domain, if
but
this answers your question.
It's a problem of security. So one thread could read cache. It's like a meltdown or something like that. It is a
meltdown is a cyber attack, but I am not sure I understand the relation to this.
I don't understand how it optimized for concurrency for that way of multi-thread for hyperthreading.
Okay.
How it's optimized.
So for hyperthreading, these threads share the same L1 cache. So if
so we have a security problem, right?
Yes, regardless of these mechanisms, regardless of recoverable systems, they have these vulnerabilities which Intel is working to correct. And once they fix one of these problems, another pops out. But but this is unrelated to this to these instructions. This problem indeed exists. The out-of-order execution indeed opened many security hazards in terms of cyber attacks, speculative execution, and Intel fixed some of these, and others are found. So
yeah, my question was about is that optimization of this concurrency?
I see. Is it resistant against? That's a good question. I'm not sure. I hope so. I guess so, but can't say for sure. So just to conclude very quickly, this may be a disruptive technology. This may have many implications. For any of you all of you took the operating system course, maybe in a few years, some parts of it will be different because, I don't know, maybe there will be no more need for paging. We still don't really see all the possible effects of this technology. And now that real systems are out there, although still very expensive, I guess the more abstract model and algorithms, we can evaluate them in a more sound manner using these systems and maybe have algorithms that are of more practical value. Thank you.
So we have time for maybe one quick question.
Okay, yeah. Very quickly, excellent question, because it's the next slide. So the first question is about this code that we have seen, the implementation of a recoverable compare and swap. So here in line 13, there is a condition that is a disjunction of two sub-expressions. So the question is, does it matter in what order we evaluate these two sub-expressions for correctness, or does it not matter? I will also send a PDF with these questions. So the second question is that we saw this n-process tournament tree recoverable algorithm, and we said that the exit section is performed by having the process go down from the root to the leaf, releasing all the 2 out of n locks along the way. The question is, if the process would do that, the exit section in the opposite order, coming from the bottom up until the root, will the algorithm still be correct? This is actually more of a mutual exclusion problem, not necessarily related to recoverable mutual exclusion, but still interesting to think about. And the last exercise, which I need to solve myself first, but it's doable, at least I hope so, is to extend the recoverable concurrent swap algorithm so that it will also support write operations, not only read and concurrent swap, and will still remain linearizable according to the definition that we saw, according to NRL. And I think it will be quite complicated if you try to use only read and write and CAS operations. So you can also use a simpler operation, memory swap, that takes two shared variables and switches their values.